হ্যাঁ কি
করতে পারছিস কি?
হ্যাঁ স্টার্ট হয়ে গেছে রেকর্ডিং।
ঠিক আছে, বন্ধ করে দে এবার।
বন্ধ করে দাও, হ্যাঁ, নাহলে বড় ফাইল হয়ে যাবে। Hi, welcome everyone. So we'll just wait for a couple of more minutes for people to join in. So please bear with us for 2 minutes. So welcome everyone. We welcome you all to today's session. Although it's like getting quite hot in Mumbai, you may require your blankets in this talk because we will discuss some real cool stuff. Just joking, yeah. So before starting, let me make a small announcement. So you may see that we have intentionally put everyone in mute so that there is no unintentional background noise. We do have a dedicated question and answer session as well at the very end, where you may ask questions. If you may have a question during the talk as well, or speaker asks a question which you want to answer, kindly go to the participants tab and use the raise hand option. We will interrupt the speaker in due time and ask to unmute yourself. In case you are hesitant to ask directly, you may also type the question as well in your chat. We will monitor, and also if in case you have a feedback regarding how we may improve our sessions, please do not hesitate to contact us personally in any medium like email or WhatsApp. So yeah, today we have it's a pleasure for all of us to have with us Ramprakash Pandeya giving this talk. So he requires no introduction really, but still on behalf of to complete these procedures, I will briefly introduce him. So he completed his bachelor's from Banaras Hindu University and joined TIFR in the integrated PhD program in 2015. He is currently working under the guidance of Professor Kalabran Maiti in the electron spectroscopy lab and has done some really exciting works. He will take all of us into his world today. So every one of us knows that the prospects of high temperature superconductors can be really cool. So he will talk about one such endeavors in this session with a specific type of superconductor. The title of his talk is Photoelectron Emission Spectroscopy Study of Iron-based Superconductors. So without much delay, I would request Ramda to just start. So the floor is all yours, Ramprakash da.
Thank you, Subhajit. So before I will start this talk, I would like to thank Subhajit, Somak and Akash for giving me an opportunity to give a talk on this journal club. So my talk is based on the photoelectron emission spectroscopy study of the iron-based superconductors. So, so the plan of the talk will be basically I will provide a brief history of these iron-based superconductors and then just say a few words on the superconducting properties of these compounds and then say a little bit about the technique that we are using in our lab to probe the electron structure of these compounds. And then I will show a few slides on our study that we have carried out. So these are basically 1 to 2 compounds and we have doped electrons. We have doped electrons at iron site of the compound. And we studied the electronic structure using hard X-ray photoelectron spectroscopy, which is also known as HEXPS, and the angle result photoelectron spectroscopy, which is basically the RPS technique. So what are these iron-based superconductors basically? So these in 2006, people actually found superconductivity in the LFEPO compound, and they didn't pay much attention because there are already many nictide compounds. So nictides are basically the compounds which had phosphorus, arsenic, antimony, and there are chalconite compounds also like selenium and tellurium. So since there are already many there are many nictide type of superconductors, people didn't pay much attention to these compounds. Later in 2008, people found superconductivity in LaFeSO by replacing oxygen with fluorine atoms, and they found that the Tc value actually it went up to 26 Kelvin. And so people started looking at these compounds. Till that time, people called these compounds as a nictide compounds because most of the compounds that they studied, they had arsenic or the phosphorus in these compounds. But later, when they did the electronic structure study, they found that the near Fermi states, which is also known as a valence band. So the density of the state in the valence band was mostly constituted by the iron. So then they started calling these compounds as iron-based superconductors. Now, after intense research on these compounds, people found that there are actually many types of iron-based superconductors. Although they have different number of elements, they have similar structures and similar properties. So then they basically categorize these compounds in different families. So 1,1, 1,1,1, 1,1,2, 1,1,1. So it's basically depending on the stoichiometric ratio those elements have in these compounds. So similar to the copper-based compounds, these compounds also have many common features. So one most important common feature is this quasi two-dimensional iron nictide or chalcogenide layer, which is a conducting layer, and other layers which I can say in 1 to 2 compound is calcium layer, or in 1,1 compound La or oxygen layer. They don't play much close to they don't have any significant amount of density which is close to Fermi energy. So mostly the conductivity or superconducting phase that we observe in these compounds comes from the quasi two-dimensional layers. In case of cuprate superconductors, it was copper and oxygen layer. Then one interesting point that I should make here. So like in copper-based superconductors, this copper and oxygen layers were almost two-dimensional. I mean, if you reduce the two-dimensionality, if you make it almost three-dimensional, the superconducting phase becomes little bit difficult to find. But in this case, actually, the superconducting phase appears only if the iron arsenic or iron nictide bond lengths are around 1.4 angstrom, and there is a bond angle also. So the bond angle never goes to 180 degrees. Now, these compounds also have other properties. So like most of these compounds are C4 symmetric and paramagnetic at room temperature, and you cool down below certain temperature. So temperature depends on compound that you are studying. So it basically goes to a different structure with different magnetic ordering. So this the lower temperature state is a two-fold antiferrometric state. And if you dope electron or hole at different sites of the compound, you basically can tune the properties of the material. So the magnetic structure, magnetic transition that you are expecting in the parent compound, that suppresses with the electron or hole doping, and then you observe a superconducting phase within a critical doping range, which is also known as a superconducting dome. Usually people also find in copper-based superconductors. The interesting part in this compound is that the superconducting phase and the antiferrometric phase, both phases appears in, there is a part of the phase diagram where both these phases coexist. Well, people don't know why these phases coexist in these compounds. And we're looking at this thing. Because of this coexistence, people think that probably the pneumaticity in the compound or the spin fluctuation is responsible for the superconducting phase in the compounds. Other thing that the different thing that these compounds have is the number of hole pockets or the electron pockets in the Brillouin zone. So in copper-based superconductors, the number of pockets that you have in Brillouin zone is only one. However, in these cases, you have five pockets. Two are electron pockets centered at the M point, and three at the hole pockets. Three hole pockets at the gamma point. The other hole pocket is not seen here because that one is actually degenerate at these range, at this binding energy range or at the Fermi level. Now we also have a Q vector. This Q vector is basically a nesting vector. This nesting vector is actually related to this point next few slides. So what are the superconducting properties? So of course, these are unconventional superconductors, and they have a superconducting dome very similar to copper-based superconductors. And unlike other superconductors, there is a part of the phase diagram where the superconductivity and the magnetism both coexist. The TC that we observe is very sensitive to the iron nictide chalcogenide height or iron nictide iron bond angle. So nictide height, where it shows maximum TC value, this compound shows maximum TC value is around 1.4 angstrom, and the bond angle is around 103 degrees. So if you change little bit of these angles or the bond angle values by applying pressure or replacing an atom in this compound, these bond angles will change, bond angle or bond height will change, and the TC will also change. Now the gap symmetry in these compounds is S-wave type, very opposite to the copper-based superconductors, which is D-wave type. However, these are not conventional superconductors, so we cannot correlate these S-wave type superconductors with the any question? S-wave type with conventional VCS superconductors. We also do not, in these compounds, we do not observe the pseudo-gap phase, which people usually observe in unconventional copper-based superconductors. The most complex part in these compounds is the large band renormalization factor. So renormalization factor is basically, if you do the DFT-based calculations, compare with the experimental data, experimentally measured electronic structure, and if the renormalization factor is 1, so it means that there is no correlation in the compound, the calculated electronic structure will match with the experimentally measured electronic structure. However, in these, if there is a correlation in your compound, you'll always find that the bandwidths will be different in the experimentally measured electronic structure, and then people usually multiply some factor to match it with the experimental data. So these compounds basically are showing that there is a huge correlation in these compounds. Of course, it is iron 3d orbital. Still there is a huge renormalization factor, and this the renormalization factor also actually varies with the band orbital character. So like few bands have DXY character, the band which has DXY character, they have larger renormalization factor in comparison to the other bands. The superconducting phase and the enhancement of TC with magnetic doping such as cobalt, nickel, and the orbital band renormalization are still an open issue in these iron-based superconducting compounds. So what can we do with the photoelectron spectroscopy study? So with photoelectron spectroscopy, basically you can directly probe the electron structure of the compound in its different phases. So like at room temperature, it is tetragonal, so you can measure it there at that temperature and then measure it low temperature also, and then you can dope it and then again measure the electron structure and see how the electron structure of this compound is varying with different parameters. You can also measure the orbital characters. The orbital characters are basically if you have a band, so there will be a character of different orbitals. So like d orbital character can be there, different d orbital characters. Those characters also can measure by changing the polarization of incident light or the changing the photon energy. You can measure the number of, we can measure the nature of the Fermi pockets also, like how many Fermi pockets are there, what is their dimensionality, what are the symmetries that they have, what is the size, how they are evolving with temperature, and what are the dispersion relations that you can of course measure it using pH technique. You can also measure the gap symmetry. So you basically do the kx-ky plane mapping as a function of kx-ky plane mapping, and from there you can find the superconducting gap symmetry. Gap symmetry in this superconducting compounds is very important parameter. And this technique is, I mean, using this technique, people actually confirm that copper-based compounds have D wave type of symmetry, and in this case, it is S wave type of symmetry. You can also measure, observe the temperature evolution of the gap states. I mean, how the gaps are closing at different K values for different bands. You can also extract the electronic self energies as a function of momentum and temperature and compare with the theory. So the self energy basically comes from the many body interaction part. And in first general club talk, I think Arindam has discussed these things that you can, if you have the photo emission spectra, by by calculating the bandwidth of the bands, you can calculate the self energy as a function of different K values and the momentum also. Now, what is the photoelectron emission technique? So it's very simple and complex. Simple in the sense it's based on the photoelectric effect. So basically shine a light on the sample, electron will absorb those photons, and it will come out from the sample. And if they, of course, it will come out only if the kinetic energy, if the incident photon energy is sufficiently high. So if I define right side of this part, samples electronic structure. So you have very sharp features which are basically the core levels, and then you have a very sharp cutoff at the Fermi energy also. So below these states are filled. Now, if you excite it using a photon energy H2, these states will basically get to here, will go here, and then you will get the spectrums. Now, the broadening of these features are basically due to the lifetime of the particles that your hole creates, the hole that you have created, and also the resolution of the spectrometer. The broad feature that you see here, it's mainly due to the Fermi-Dirac distribution of the function at a finite temperature, and of course the spectrometer resolution that also plays a role for this type of feature. Now, once you know the kinetic, once you know the intensity as a function of electron kinetic energy, you can use this equation and then find out the binding energy. So you can get the binding energy of different states as a function, intensity as a function of binding energy. If you have also measured these electrons at different angles, so which is basically the technique is basically angle resolved photoelectron spectroscopy technique. So in that case, you can also calculate the momentum of the electron that is coming out from the sample. And if you change the photon energy, so if you're changing the photon energy, you're basically changing the kinetic energy of the electron, and that means you are basically changing the kz. So by changing the photon energy, you can also map the, you can also change the kz momentum, and in that way you can get the whole Brillouin zone of the system. You can map the whole Fermi surface of the system, of the interstate system. Now, the intensity that we measure, it basically depends on these four factors. So this upper factor is basically from the Fermi's golden rule. So you are exciting electron from initial state psi I to a psi f. So psi I is basically the state that we see here, and psi f are we usually consider it as a free electron state, but it can be a complex state also, depending on what kind of study you are doing. The lower these denominators are basically due to the sigma that you see here, it's because of the imaginary part of the self energy coming from the many body interaction, and the gamma is the real part of the self energy, and these parts also gives finite broadening of the bands. that we observe in the photoelectric spectroscopy measurements. The Dirac delta function is basically ensuring that the energy is conserved. You can also write a momentum conservation Dirac delta function. The third part is this exponential e to the power minus x by lambda part. So this basically comes due to the electron inelastic escaping. So when you are exciting an electron, say x distance from the surface, it will have to travel that much distance to come out from the sample. And while traveling that much distance, it can get scattered from the other atoms, impurity atoms or electrons or something else. And that way it can lose the information, it won't be able to come out, or even if it comes out, it will give a background. So in that case, the probability that it will be able to come out will be e to the power minus x by lambda. It's basically Poisson distribution, where lambda is electron mean free path. Now this is basically a mean free path as a function of electron energy. So as you can see, it follows a somewhat parabola type of shape. It's not a parabola, but somewhat parabola still. So it shows a minimum value at within this 50 to 100 eV range, and at this range you can see that the mean free path is around 5 angstrom. So because of this mean free path, the technique that we use is very surface sensitive. So if there is anything on the surface, just one layer of the oxygen or something else will make things worse. So we won't be able to see anything from your sample. We'll basically get the count from the upper impurity level. However, if you increase the kinetic energy, so like if you go to 6,000 or 8,000 photon energy, so the kinetic energy will also be close to those photon energy values. So in that case, the mean free path will be around say 50 or 60 angstrom. So even if there is a small layer on the surface, it won't matter much. But just to be precautious, we actually always cleave our samples inside the vacuums where the pressure is around -10 torr.
Just interrupting briefly. So there is a question in the chat. So Joydeep is asking that for superconducting samples, will the Cooper pair break to have photoelectron emission? So that is the question.
Yeah, of course, it breaks. So when you break these Cooper pairs, because of this binding energy of these Cooper pairs, you get intensity at that much energy. So you will basically see a sharp feature at delta gap value. So say the delta gap value is say 10 MeV, you will see no intensity from Fermi energy to 10 MeV, but you will see an intense feature at the 10 MeV. So of course you break the Cooper pairs also.
Okay, I guess that answers Joydeep's question. Just a minute, I will just, okay, he says that it's fine. Okay, so there is another comment from Biplav that whether the superconducting state should be S minus wave or it should be S plus minus.
So yeah, I can see the question. Of course, it is not purely S wave type. It should be either S plus. There is a phase with the superconducting gap. Why didn't say that part? Because no one actually has measured that. So till now we are able to measure the gap as a function of momentum, not the phase of the gap. So that's why, of course, theories which are there to explain the superconducting, they are not pure, proper theories, but still they provide a gap symmetry in these compounds. So those theories says that there will be a phase with the gap value, but till now no one has measured it. So that's why I didn't say that it is S plus minus or S minus type of superconducting gap. Of course, its function is something like cos kx, cos ky. So if you go to different coordinate, kx, ky coordinate, you will see that the gap value will have positive phase, whereas in other coordinate it will have negative phase.
Yeah, Ram, I have a quick question. Like I don't know much about things. So what do you mean by the phase of the superconducting gap? Can you briefly explain, like you explain to a BSc student?
Okay, so this delta gap usually we define. So in BCS type, okay, I guess in BCS type also we define this. There is one chapter in this book, so I don't remember that part. But of course, so the delta that we define, actual delta value is delta mod of delta as a function of k, and then we define a phase e to the power I phi k. So usually we consider that BCS type. I don't remember whether this phi k gap will be finite or not, but of course the delta mod of delta k is independent of k. Okay, probably I couldn't answer your question, but I will look into it and then I will give a statement. Yeah.
Okay, Ram, I think you can proceed. There is no other questions I can see right now.
Okay. So since all these iron-based superconductors share similar type of common share similar type of properties, so we basically looked at the CF2S2 compounds 122 type iron-based superconductors, parent compound of iron-based superconductors, and if this has basically this both structural and magnetic transition, as I discussed in the first two slides. It shows this transition at 170 Kelvin at ambient pressure, so it basically goes from tetragonal to orthorhombic phase. We have this iron arsenic quasi 2D layers. So when it goes to this phase, the local moments which were there at the iron sides, they are now aligned in an antifermatic arrangement. And as you apply some pressure on these compounds also show a different type of structural transition from tetragonal phase to collapsed tetragonal phase. And interestingly, this collapsed tetragonal phase has no local magnetic moment ordering, whereas of course this iron is expected to have local magnetic ordering. Within this small pressure range, it also shows a superconducting phase below 10 Kelvin. However, people are still trying to understand, I mean, which particular phase is responsible for the superconductor, whether this pneumatic fluctuation coming from the pneumatic or the Swiftsian fluctuation coming from the orthorhombic antifermatic phase is responsible for this one, or the CT phase is responsible for the superconducting phase in the compound. Doping electron or hole at any three positions. So electron or hole doping means basically you replace the iron atom or arsenic or the calcium atom with similar radii atoms. In these conditions, you can also get superconducting phase at low temperature and at ambient pressure. So we basically wanted to see, I mean, what are the things that this, so in our case, we actually chose this cobalt doping at iron side because of obvious reasons. I mean, these, if you dope cobalt at iron side, you can get very big crystals, very big high quality crystals, so size of 6 to 7 mm by 7 mm. And because of that, we chose this compound. We just wanted to see, I mean, what kind of changes this electron doping at iron side can give in electronic structure of the compound. So for that, we basically studied the electron structure of both parent and the cobalt doped compound. Now, first we looked at the angle integrated photoemission spectra. So this is basically angle integrated photoemission spectra in valence band region using hard X-ray photoemission spectroscopy. So the open circles that we see is from the from CaCO122 compound, and the lines are from basically represent the Ca122 compound. Ca122 is basically CFE2S2 and CaCO122 is a cobalt doped CFE2S2. Now, what do we expect from the electron doping? So if I take this as a without doping compound, you will have a Fermi edge, and this is the core level, this is the valence band, and there is a Fermi edge. So states below this are filled. Now, if you dope electron, you will basically fill electron allowed or unoccupied states above Fermi energy. So now you will have new Fermi energy, which will basically lie somewhere here. And just to align the Fermi energies in these two compounds, you will basically see that if you compare these two spectra, you will see a small shift in the spectrum. So usually people compare the core level spectrums and see whether there is a shift in the core level or not. If there is a shift, it means that you have doped electron, and if there is no shift in the compound, it means there is no electron doping or there is no charge carrying doping in this compound. But since we have doped in, we actually expect that this kind of feature should appear, which was not in the case. And same thing we can see here also. I mean, there is no significant change in the main core level spectrum. There is small change at this position, but this is because of the surface state that we observed close to this energy value. If requires, I can discuss about it, but let us not discuss about it. So this is basically so just to understand why we are getting these things here, we looked at the RPS spectra of this parent compound and the cobalt doped compound. So this is the raw spectra, and this one is the double derivative. So a little bit is smoothing and the double derivative of this spectra. And we can see nicely these three bands which are crossing the Fermi energy. I'm sorry, one band crossing the Fermi energy, and one band is just going to the Fermi energy, and another band is showing this type of feature. Actually, this band is also expected to cross the Fermi energy, because of the SDW phase ordering, it shows a back band folding, which I can discuss here. So what happens that if you have a normal, if the temperature is above this Tn value, Tn is basically antifermatic ordering temperature. So in that case, you have this vector of A value, this is basically the translation vector or lattice vector, and because of that you get a band using tight banding model. Now if there is a transition, so in this case we have a spin here, a spin down here, a spin up here, so now the lattice vector is now twice of the initial one, so you will basically get the Brillouin zone is smaller than the earlier case, and because of that these bands which were here, now they have moved to this position also because of the lowered symmetry. And since these bands are crossing at these energy values, because of the lattice potentials, you will see this lattice potential will basically create a gap at this energy. Now if I zoom it in from pi by a to pi by a only, means within the first Brillouin zone, from here to here, I mean, I will, if the above Tn it was like this, below Tn I will see this type of feature. So this is basically the reason why we see a back band folding in case of CFE2H2 case. So okay, yeah.
Ram, I had a quick question here. Like, yeah, if you look at this kind of color scale plot, so my question is from an outsider. Like, so when we look at this kind of color scale plot and we look at some overlaid lines, so sometimes we don't really see them to be very clear in the color scale plot. So my question is like, so to draw this overlaying line, do you take some theoretical input, or you do really some analysis, like fine analysis on the experimental data to know the lines?
So of course we require electron structure calculations from DFT, but we also do one thing, we basically draw these EDCs, EDCs and MDCs. So MDCs are basically the momentum distribution curve as a function, momentum distribution curve at different binding energy value. So if you draw a curve, even if you are not able to see a band, suppose in this case you can't see a band here, if you draw a EDC value, you will see a small feature at those positions, and those features will actually move with the binding energy value. So by fitting those features, we actually draw these curves. But of course, we also compare these things with the theoretically calculated electron structure. Otherwise, it is very difficult to find the position of the bands or the number of bands itself actually.
So basically, if I understand correctly, let's say to draw these green lines, so you are not depending on just these color scale plot, but you are depending on more data from your experience, right?
From electron structure calculation also. So like from electron structure calculations, we know that there will be 3 pockets at the gamma point, and this part we don't expect in the electron structure calculation because there is no lower symmetry. I mean, we didn't put any reduction in symmetry of the compound while doing the electron structure calculations. So this part we don't expect. So it means that this part is coming from the thing that we are not included in the calculation. So that part is basically the anti-parametric ordering, that it's difficult to put this anti-parametric ordering in the DFT calculations. So based on those things, we are basically saying that this part is coming from the anti-parametric ordering and the back band folding of the beta band.
Okay. Okay. Thanks.
So then we looked at the electron structure of the cobalt doped compounds. So of course it would be difficult to say from here. So here we can see, so this one is basically the zoom of this part, zoomed on of this part. So okay, this one is also the same thing, but taken a different photon energy value. We see a nice band which is going like this, and there is another band which is going like this, and close to here there is another band. So what we are basically seeing is that while in the parent compound, this band, so both these alpha and the gamma band were bands were crossing the Fermi energy. In this case, we see a significant shift in this position of the bands, and this shift is expected in the sense that, I mean, if you dope electron in your compound, the states will be filled, and then since the states are filled, the Fermi energy will go up. However, the main problem is that the position of these p states. So even if you fill the electrons in your compounds, basically dope the electron in your compound, position of these bands was expected to appear very close to each other. However, we see that in this case, the alpha band is much at this position, whereas the beta band is still close to the Fermi energy and gamma band is still crossing the Fermi energy. So what I did is basically I drew these lines using this normal parabola equations, h cross k square by 2m, and from there I calculated the m star value. So since I know that the bands are almost parabola close to the gamma bands, I could draw these things, and from there I calculated the m star value.
Sorry to interrupt. I have a small question. So, can I ask?
Yeah, ask.
Yeah, so since your sample is superconducting, so there will be one superconducting energy gap, let's say,
Yeah, yeah.
and also due to some antiferromagnetic ordering, some other gaps are open.
Yeah, but in this case, there is no antiferrometric ordering. I am so the concentration that I have chose, the cobalt concentration that I chose, it basically leads to suppression of the complete suppression of the antiferrometric ordering. So in this compound, we don't have any antiferrometric ordering.
Okay, so there are many different kinds of band also here. So these bands are within the band gap of the superconducting energy gap, or I mean, what is the different energy scales here? So see, since your sample is superconducting, there will be an overall superconducting energy gap. Also, due to interaction, there are also many
No,
gaps.
but gap will appear at even low temperature actually. So it's not at 10 Kelvin. The gap will appear below, I guess, 8 or 9 Kelvin temperature. And
Okay, so
gap value
at
is
this
very
point, the
small.
sample is non-superconducting.
No, yeah. And also the gap value is very small. So usually these gap values are order of, I mean, if the transition was say 20 Kelvin, and if I'm measuring at say 15 or 10 Kelvin temperature, then that time the gap value will be order of say 5 or 6 MeV. So it's very difficult to see from here actually. If you want to see the gap, if you want to measure the gap value, then we'll have to zoom it very close to the Fermi range. So within 100 MeV, we'll have to zoom it and then try
Right.
to fit it with the
Yeah. So that gap is very small.
Yeah, of course it's
Few
very
MeV, and that is in
Yeah.
EV. Okay, fine.
So Ram, just to understand what you are doing here. So basically, in the panel D, you are plotting the band structure, and you like where like near the gamma point, near the red peaks, you have 3 bands there. And now in panel A, you are trying to understand, like identify those bands, right?
No, so actually I was going to talk about this band. So this part. So this part is basically the electron structure calculations using DFT. Since these band positions were not matching, I actually multiplied some renormalization factor, and still I see that these band positions are not this exactly the same way as I am expecting at this position. So it means that these DFT calculations are not good enough to capture the things that we measure in the cobalt doped compounds. So basically what I want to say is, I mean, with the cobalt doping, what do we expect? We basically expect that the Fermi energy will shift, the whole bands will go down. However, in this case, we see that the bands are not going down. I mean, some of them are going down, but most of them are not going down. So it means that it's not just, and the doping of this replacing iron with cobalt is just not leading to charge carrier dropping. It is actually also creating significant amount of correlation in the compound, which is not well captured in the DFT calculations.
Okay.
Ram, there is one comment from Biplab and question. So what is the doping level and TC of the doped material, and do you have any bulk data?
Yeah, so this transition temperature actually up. So I have done magnetic measurements. It appears around 10 below 10 Kelvin, I guess. I have done this magnetic measurement, magnetic susceptible measurements. It appears below 10 Kelvin.
Okay. So I think that answers the question. So he has another comment. So he says it is not clear if underdosed or overdosed sample.
It's not overdoped actually, because overdoped means you are very It's difficult to say from here because there is no phase diagram for this compound, I guess. Because in order to find whether it is underdoped or overdoped, we basically get this superconducting dome, and then try to find out at what if the doping is very close to the other end of the superconducting dome, then we call it as a overdoped sample. And if it is close to the antiferrometric ordering and superconducting phase, then we call it as a underdoped compounds. But since I don't know whether there is any that kind of phase diagram is available for these compounds or not. So if it is available, then we can say whether this compound is underdoped or overdoped. Okay, so if he knows, then he can tell me actually.
Yeah, I think means you can contact him and we can continue. Yeah. we can continue the talk now, and maybe after talk means you can personally contact develop the like postdoc. Okay, thanks. Yeah, Adam, you can continue.
So what we basically see is that with cobalt doping, we are not only just doping electrons in the compound, we are also increasing a significant amount of correlation in the compound. And that's what I basically wanted to say from here. What else we actually see? So this is basically the Fermi surface mapping of the Fermi surface mapping. So photon energy is, as I said.
Hello, Ram.
Yeah.
Sorry to interrupt. I have just quick question. So you told that correlation present in the system, right? Just last slide.
Yeah.
Yeah. So how to justify that means how the correlation for this system from the RPS data?
No, what I meant by the correlation means the DFT calculation that we do. It in this case, I have not included the correlation part. So there we basically these calculations are basically single particle calculations. So we don't have correlation in these calculations. So you basically add U from outside and then you include the correlation part. How do I know that in this compound there is a correlation or not? So it's basically because the dispersion relations for these bands are not matching with the experimental data. And the M star values that I'm getting from the calculation are much lower than the experimental value. So M star is high whenever there is a large correlation. So M star is high means that when you are, so I can go to the last slide actually. So what I mean, M star is how M star is basically varies. So suppose the electron is trying to hop from one position to the other position, okay, and if the U is very high at this position, so it means that it won't be able to go there, okay. So if it's not able to go there, your hopping parameter will be small, okay. So hopping parameter is small means that the bandwidth will be small. So if the bandwidth is small, if you calculate the M star value, this M star value basically depends on 1 by T. So how it depends? So this EK relation that you have is basically E for one-dimensional chain, E 2T 1 minus cos Ka. Okay. So if T is so E equal to 2T minus 1 minus cos Ka. So M star is basically 1 by D2E by DK2, and H cross square factor is also there. So ultimately M star is directly proportional to 1 by T. Okay. So if T is small, M star will be large.
Okay.
So what I'm basically saying that if I do the calculation without including the correlation, in that case, the M star values are smaller than what I'm measuring here, what I'm calculating here.
Okay.
So in that sense, I'm saying that the correlation is much even with the cobalt doping, I'm getting a little bit of correlation.
Thank you. Okay.
Yeah. So why we did not see any shift in this case? So that part we can say from this figure actually. So suppose there was one band which was so this green one was the parent compound case. Now when I when I replace iron with cobalt, I basically are you able to? Okay, I think it's good. So when I dope the electron at this position, I see that these bands are now renormalized. So the bandwidth is small. So the density of state will basically go up. Since density of state is high, I can put more number of electrons within this small region. In such, I mean, there is a possibility that while filling these states, the Fermi energy in these two cases will remain at the same position. And that will basically lead to negligible change in the binding energy position of the higher binding energy state. So higher binding energy states means that the higher binding state of the valence band or the core level. So in that way, even if there is a electron, even if I doping electron at iron side by replacing iron with cobalt, due to the band renormalization, I won't be able to see any change in the binding energy position of these higher binding energy states. What else do we get with cobalt doping at iron side? So as I said, these layers, these iron and arsenic are the only layers which basically contribute close to the Fermi energy. Now, when I'm doping cobalt at iron position, since the cobalt has a smaller atomic radius, So because of that, the hybridization between the iron and arsenic will increase. At the same time, the bond length between the iron and calcium will also decrease. And due to this decrease in the iron and calcium bond length, there will be significant amount, I mean, you can expect a significant amount of hybridization along KZ direction, which was not present in the parent compound. And that can actually lead to a KZ dependence of the bands. So in parent compound, we did not observe any KZ dependence. However, in cobalt dope compound, what we see is that while the alpha and the delta bands, so I'm calling these bands as alpha and delta bands. So this delta band is almost flat as a function of photon energy. So photon energy is basically related to the KZ value. So it's almost flat. Even alpha band is also flat. So it means alpha and delta bands are at least not showing any KZ dependence. Here also we see that the beta band is almost flat. So it means beta band is also effectively two dimension. However, the gamma band position actually moves with function of photon energy. It means that at least gamma band has a significantly high KZ dependence in comparison to the other two alpha beta bands. So cobalt doping is also affecting the KZ dependence, also introducing the KZ dependence in the gamma band, which was actually effectively two-dimensional before doping. So here I'm basically showing the same thing. So the spectrum taken at different photon energy. So in this case, the spectrum that I'm showing in the next slide are basically taken at different these lines. So these different lines are basically these spectrums. So I'm showing here basically the same thing.
Hello,
The only
Ram.
thing is the different is that.
Hello, Ram.
Yeah.
Yeah. So this calcium
Yeah.
Fe to AS2, this is it has 3D Fermi surface, right? Or
No. Parent compound has 2D Fermi surface.
2D Fermi surface. Okay. So for this case, this FeAs basically layers are contributing in the transport.
Mostly iron actually.
Okay. Thank you. You continue, please.
But with cobalt doping, we are seeing that somehow this gamma band actually gets significant amount of KZ dependence also. It has KZ dependence also. The other thing that we see is that while in parent compound, when we did the RPS measurement, we actually observed that the gamma band, I mean, all these bands are dispersion of all these bands remains same at different photon energy or different KZ values. However, we see that in this case, the dispersion of the gamma band actually varies with different photon energy or different KZ value also. So this is the third observation that we have in this compound. So the cobalt doping is shifting the band positions, which is expected because of the charge carrier doping. It's creating huge amount of correlation that basically leads to renumeration of the bands, and it's also changing the dispersion or the renumeration factor in different renumeration factor at different KZ values. This is kind of a bad example for photoemission spectroscopy technique. So what is basically happening is that I did this measurement in our lab at 15 Kelvin temperatures at different at 15 minutes gaps. So this one is the same gamma band. We have a hole pocket here, alpha band, and we have a significant amount of intensity at this position also. So this intensity is majorly due to the surface state. So when we do this measurement, after every 50 minutes, I measure the spectrum, and we can see that the position of these bands are actually shifting with time. So these are basically surface states, and probably because of the oxidation of the surface state, we see this shift with time in this compound. So even if we have -11 torr pressure in our chamber, -10 torr pressure in our chamber, we do see a significant amount of the change in the surface state of the compound. Now, since there are already studies on these compounds, in similar compounds, BFE2AS2, and there they have found similar type of surface state crossing at this energy. So we are expecting that these lines that I've drawn here, the surface state that I've drawn here, is because of the 2x1 type of surface reconstruction, and because of that we are getting this type of dispersion, this type of surface state. So with this, I will conclude my talk. So what we have done is basically so first I gave some brief discussion on the iron superconductors. In this last 4 or 5 slides, I basically discussed about the effect of cobalt doping at iron site, and we basically measured significant band renormalization and shift of the top of the whole pocket with replacement of the cobalt doping. We also observed that only gamma band is crossing the Fermi energy among other three bands which were crossing the Fermi energy in the parent compound case. The band, the negligible shift of the valence band on the core levels that we observed using Hexpius technique is because of the combined effect of the band renormalization and the electron doping due to the cobalt atom substitution at iron side, which basically we confirmed using RPS study on both by comparing the RPS spectrum of both compounds. Since the gamma band has maximum majorly DXY orbital character, so we are expecting that probably the band renormalization factors are large for the DXY character bands. This people have found in other iron-based superconductors also. So recently in 2020, I guess, so people have done measurements on other iron-based superconductors where they have found that the DXY character bands does show a large renormalization factor. We also observed that the renormalization coefficients varies at different kz values. So if you change the kz value, the renormalization factor at some point it becomes almost 1. It goes close to the 1 value, but at the other values it is very high. The gamma band, which is crossing the Fermi energy, it also shows a 3-dimensional behavior with cobalt doping or wide temperature range. And we also observed surface states in this compound, and by comparing the other earlier spectra, we basically concluded that the surface state that we see in this compound are majorly due to the surface reconstruction of 2x1 type. And with this, I will stop my talk. Yeah. Shubhajit.
Shubhajit actually got disconnected from the talk, so the question. Yeah, so the question answers session, the floor is now open for questions, and it was a very nice talk, Ramda. So it was a very enjoyable talk. So now let's see, let's take the questions that people have. So you may ask questions by raising your hand, and we'll unmute you one by one. So yeah, it's open for the questions. Okay, so I don't see any hands. So I guess you guys are all muted. So the way to go about asking questions is that you can press the raise hand option. So if we see the raise hand option, then we'll ask you to unmute, and then you can go ahead with your questions.
Hello, Ram. Yes. So in here you doped cobalt in 1-2 system, right? So I mean, this is very stupid question. So here is somehow you doped electron, right? So in any other way means by doping, the superconducting transition temperature has gone down for this case.
Doping means okay. So if you increase the cobalt doping, probably the superconducting transition will go down. Actually.
Yeah. So by any other, do you expect any other kind of doping can increase the superconducting temperature for this compound?
Yeah. People have doped at all three sites actually. So at calcium site, iron site, arsenic site. I think at iron site people have doped 3 to 4 elements. Okay. So I remember, this cobalt, nickel, iridium.
Yeah.
Early, I think PT also. So yeah, 3-4 elements people have doped. Among these 3 actually show superconducting phase, but other element doping doesn't show any superconducting phase. Of course, it suppresses the magnetic ordering, but doesn't show any superconducting.
Yes. This 1-2 compound is stable, but 1-1 compound is not stable. right?
I don't know, but they are stable actually in the sense that people have looked. So
Very
there is
low
another
doping.
interesting part of these compounds. So because in these compounds, both iron d orbital and arsenic p orbitals contributes close to the Fermi energy. There is a chance that you will be able to see a band inversion, and because of that, in these compounds, people have found all type of topological states. I mean, till now, people that we know, all the states, topological state that we actually know till now. So, like I have seen papers where people have found these Dirac states, Majorana states, the Majorana bound state basically, and I don't remember whether people have looked at the Weil cell metal cases or not, but
In 111 system.
yeah, 111
Okay.
lithium iron arsenic.
Okay, a lithium iron arsenic. Okay.
Yeah.
Yeah. Okay.
So
Thank
recently, it is famous for these compounds are also famous for something else. So for the topological studies.
Uh-huh. Okay. Okay.
Just
Thank
for
you.
the information in the current purpose, there was a nature review. If you have a found time, you can look at it. There is a magnetic and the superconductor interface, or that which is called the Majorana mode. But how they are distinguished, it is Majorana mode.
Yeah, so it's still a open question. So mostly what they do is they look at the band inversion and just confirm.
Yeah, that is
the
a zero
topological
bias.
state.
At the zero bias conductance, you have some peak, but doesn't mean that it is a Majorana
Yeah,
mode. What is the
of
people
course.
are dream thought of so many long years. I think
Yeah,
that
so
this
I
shop
know
is
that
going
part.
to now stop,
Uh,
and people will may think about in a different way.
Yeah, so I've seen that paper actually. So I've seen other papers also. So in most of the cases, they basically do the STM measurement, STS measurement, and they see a zero bias state, and then define that zero bias state as a Majorana bound state. But of course, there could be other reasons also for the
Yeah,
zero.
that is not a true. Now it is very clear.
It is clear now.
Yeah, it's quite because see, when you have to call it, because there is also entry bound state, and you have to
So
see also the temperature evolution as well as the magnetic evolution, and none of the paper so far which is published, they have reported. They have, whenever they have seen the peak, they have just reported this is a Majorana mode. They never seen the temperature evolution or the magnetic evolution where you can distinguish between an entry bound state and between the other which is you claim of. So, but apart from that, I have a one question in the in your photoelectron spectroscopy, which is if you do the gap measurement, what is the bordering parameter generally value? What is the Dines parameter value in your case?
Dines, I think you basically are talking about that equation
See, in
that we
this
have
case, you are
1 by
doing on
gamma
the
is equal.
finite temperature measurement as well as you are embodied the photons. So there is obviously a non-equilibrium heating also there. So if you do the low temperature measurement, so in that case, what is the gamma value? Means BCS that your model cannot fit that this density of state evaluation.
No,
In that
actually, I've
case, you
never
need
seen any paper where people have calculated that part. So mostly they fit it with only one function, only with that Dirac, that superconducting gap function only. They don't fit with the this gamma part. I think you're talking about that formula, that I gamma by delta minus
that has
sigma
to be
whole
there
square plus gamma square.
because it is not possible otherwise at the finite temperature.
No, so the problem is as I showed in one slide. So like because of the photo emission spectroscopy technique itself, you can have that part in your spectrum, and because of that, it's difficult to say whether that. So this part I'm saying in spectroscopy, in this technique itself, you have this gamma and sigma part because
Yeah,
of
that's
the
what is the value of the
whole.
gamma generally comes as, because you are measuring the low gap superconductor, because that's why I'm asking, because it's a high gap. Let's say if you have like a 3 millivolt or like a 3.5 millivolt, like a bulk superconductor measurement, there you can compromise. But wherever the 1 millielectron volt gap value, or let's say the 0.8 or the 0.9, there the gamma is like a very much effective.
Actually, I've never seen any paper where they have actually calculated this thing. So I
Okay.
won't be able to comment
Sure,
on this
sure.
part.
Thanks.
Any more questions? Because right now I think the participants can actually unmute themselves. So like the last time, Shovik Da and Surajit Da, you unmuted yourselves, right? I mean, there was no need to to be unmuted by others.
Unmuted myself.
Yes, yes. So I guess if anyone has any further questions, you guys can go unmute yourselves and ask the questions.
Maybe I can ask one small question. So
Yes,
in
go
the
ahead. Go ahead.
top right panel, so some bands you have drawn with sharp like delta function like feature, and some are broadened.
Yeah, yeah.
So can you please explain that part?
So in atomic case, you actually expect a sharp line. So sharp line means that the states are not dispersive. They have finite energy value and no k dependence. So like a hydrogen case, you have for n equal to 1, you have a one energy value. It's not broad. It's not that it doesn't have many energy values. So, but when you excite these core levels, because of the resolution broadening and lifetime of the core hole that you have created, you actually get a Gaussian Lorentzian product function in place of this Dirac delta function. Now, close to the Fermi energy, so if I take if this is the valence band of the my sample that I'm trying to study. So if this is the Fermi energy, so it means all the states below this are filled. At finite temperature, I will have a Dirac distribution which basically go like this. Okay. And now when I'm exciting it, when I'm trying to measure it with the photoelectron emission spectroscopy, I will basically get this effect of the Gaussian broadening due to the spectrometer, and hence I will get a convolution of valence band spectrum at finite temperature and Gaussian function with sigma value is basically the resolution of the detector. So because of these two effects, we get this type of feature in place of this feature.
Okay, so you are saying this comes from the experimental resolution factor and other.
Which part? I mean, it has both.
The broadening.
Broadly comes because of the spectrometer and the lifetime of the core hole that I've created. So when you knock out an electron, you basically have a core hole at the sample position. Now there is a finite lifetime of that core hole. So if it has very low lifetime, you will see a very broad feature. It basically comes from the Heisenberg uncertainty principle. So if the lifetime of that core hole is very low, I mean very small, in that case, you will basically get a large broadening in the energy scale. So because of these two regions, we get broadening here.
Okay. Thanks.
So we have a question in the chat box. It is from Biplab Da. So he is asking that is it possible to probe the pseudogap anomaly with PES?
What is the anomaly in this case? I mean, pseudogap in case of copper-based superconductors is known, but in this case, no one has found actually. So what is this anomaly that is talking about? Can you ask him? I mean, what does he mean by?
Yes. So Biplab Da, Ramprakash is asking like, what do you mean by the anomaly part? Like he wants you to like kind of like make it a bit more clear for him so that he can like tackle the question properly. Like, what do you mean by the pseudogap anomaly? So could you please like type in the chat box?
We can measure in case of I mean, people have measured it. People have also found the K dependence of the pseudo gap also. So it's possible. But these iron based superconductors doesn't show any pseudo gap behavior. I mean, pseudo gap close to the Fermi energy.
Ram, I have just a quick question, just for a curiosity. That's generally this magnetism and the superconductor are the two opposite era.
Yeah.
So now, what I just want to know that what makes this iron-based superconductor has such a high TC?
Well, it's open issue actually.
I see.
Yeah,
So that's why I want to know
no one
that
actually
what
knows
makes
why
it
this.
such a high TC, because one should have been expect from the general point of view, it should be as low as possible, because even
Not
it
only
should not.
that. So not only that, I saw that with cobalt doping, I am getting superconducting phase, but cobalt itself has a finite local movement.
Yeah, that's why I'm asking that
And
what make even you at the beginning of your talk you told that this is even in the some condition it go to the 26K.
Yeah. So this
That's why I'm
iron
asking that
selenide, actually
what
this
makes
iron
this
selenide
compound
case,
such a high TC.
that part I won't be able to comment actually, because
Okay.
I mean there are no theories for these compounds. It's
I see.
exactly the same like we have for the Q-plate superconductors or the heavy fermion superconductors, where M star is like 100, 200 times of the free electron, and still they show superconducting phase. So like you expect that if the M star is very high, they won't be able to move from one position to other position, but they do show superconducting phase, which means that they can move freely inside the sample. So these are actually still an open issue.
I see.
I can tell you one example, interesting example is iron selenide. You probably know about it. So iron selenide at room temperature shows superconducting transition around 7 Kelvin at ambient pressure.
Yeah.
Light pressure you can get up to 14 Kelvin. You can replace tellurium at selenium position, so then it can go to 15 Kelvin temperature. But then if you make a thin film of this compound on STO substrate, it actually shows superconducting transition up to 100 Kelvin.
I see. Yeah, that's interesting.
So I mean, no one knows why these things are actually happening. So they're still open.
Sure.
One just last question. So in this top right panel, so just I'm curious. So in the first cartoon, so you have some core levels, also some bands. So from our basic knowledge, we know that the bands come from the interaction between the levels when we have multi-system. But in this case, how you have this core levels isolated, also you have bands. Can you tell?
No, I didn't get it. Can you repeat your question again?
So let's say I have an isolated hydrogen atom. So I have only energy levels, discrete energy levels. Now I put many atoms, hydrogen atoms, so they start to interact, and then the bands will start to form, right? So in this case, you have some core levels, which is a single energy level.
So I can give you an example. So if you have sodium metal, so you have sodium 4s orbitals outside and all unoccupied states. So basically 1s, 2s, 2p, 3s, 3p, all these states. So since these states, these core level states are isolated in the sense they are very far from the next neighboring atom. So they cannot their wave functions cannot overlap with the neighboring atom wave functions. So there will be no hybridization between the core levels of one atom to the core levels of other atom. And that's why you will always get a intense, Dirac delta type of feature for the core levels. But since the valence band states like 4s, the sodium case, they can the wave function overlaps with each other. There is a finite probability that they can move from one position to other position, and those things can give rise to the finite dispersion of energy versus K, or you can say bandwidth actually.
Right. Okay. Got it. Okay. Thanks.
Okay, so if there are no more further questions, I think we can end the session for today. And any further questions that you guys might have, might come up in your heads, you can forward it directly to Ramprakash via email or any media that he would prefer. So, okay, thanking you, Ramda, once again for this amazing talk. And we are concluding the session here. See you on next week.